Okay. In the announcement section, there is a video, and let's see if it'll actually bring up that announcements page. But on the announcements page, there's a video for, here it is, for section 3.2, and it's over completing the square. All right, so it should be here once everything loads up. I'm going to go into lecture notes, and I'm going to pull up the section 3.1 and 3.2 set of notes. All right, so in section 3.1, we're going to take a look at quadratic numbers. Excuse me, we're going to take a look at complex numbers. And complex numbers are in the complex number system. And the complex number system is an extension of the real number set. And here's what actually defines the complex number system. I, which is an imaginary unit, is equal to the square root of -1. Or I squared is equal to -1. So when you're looking at complex numbers, you're going to see this funny looking I, and this is called an imaginary unit. And we'll take a look at in a second why it's called an imaginary unit. As a fact, I is equal to the square root of -1, and also I squared is equal to -1. Right? So if you take this I equal to the square root of -1, and if you were to square both sides, you would get I squared equal to -1. Okay, which are two rules that drive this complex number system. Also in the complex number system, it requires complex numbers, and complex numbers must be written in standard form. And here's the standard form of a complex number. Standard form is A plus BI, where A is the real part of your complex number and B is the imaginary part. Okay, B is A and B are both coefficients. The coefficient of your imaginary unit is B. All right. So here's a look at some numbers that are in standard form. Okay, here we have, in this chart, we have three columns. The first column shows us the complex number, and basically the last column shows that complex number in standard form. So for example, -8 can be written as -8 plus 0i, right? And -8 is a real number because it doesn't contain an imaginary part. Next we have 0. 0 can be written in standard form as 0 plus 0i. Once again, 0 is a real number. Whenever we see the imaginary I start to show up, then we're dealing with imaginary or complex numbers. For example, 3i written in standard form is written as 0 plus 3i. So notice for your complex number, if you don't have a real part, in order to correctly write that number in standard form, you must insert a 0. -I plus square root of 2 is written in standard form as 2 minus I. Okay, notice that your imaginary unit in your complex number must come second. And then lastly, we have 8 plus I times the square root of 3, which is already in standard form. And again, since it carries the imaginary unit I, it's a complex number. All right, now we'll take a look at some problems that involve what are called negative radicands. right? And we have two examples. We have the square root of -6 times the square root of -10, and we also have the square root of -48 divided by the square root of 24. Notice that in the directions, however, they tell us to rewrite the negative radicals as imaginary units before we begin any other rules for radicals. Let's take a look at these in a little bit more detail. All right, so first we have, right, well, here's where this imaginary I comes in. And here's an example. We actually simplify the square root of 4, right? So notice, just the setup for my radical, I have my radical sign, I have my index, and if we don't see an index, it's an understood square root. And I also have my radicand, which is 4. So the square root of 4 is actually equal to plus or minus 2. Okay, so here's where that plus or minus comes in. If I were to take a positive 2 and square it, notice that I get 4. If I were to take a -2 and square that, right, -2 times -2 is also a positive 4. Right, so notice I'm able to square my radicand, square my number, and I should be able to come back to my radicand. Right, so same directions, we're asked to simplify, but this time we're given negative square root of 4. Right, so notice my radicand is -4. Right, so here my solution is not quite exactly plus or minus 2, because once you square 2, you get a positive 4, and once you square -2, it also returns a positive 4. And notice that our radicand is negative. From our setup from a complex number, we had 2 rules, and one of the rules was I is equal to the square root of -1. Okay, and we're actually going to use that here. I can take the square root of -4, and I can write that as the square root of -1 times the square root of 4, right? Because -1 times 4, -4, right? And since both of these things are like radicals, I can multiply my radicands. From our facts, we can substitute the square root of -1 for I. So this becomes I times the square root of 4. And now we can simplify the square root of 4, which is 2. So we have 2I. All right. So notice, before you perform any operations, you must rewrite your negative radical as an imaginary. Right? Okay, so let's take a look at those examples. All right, so here was the caution. I'm just going to put that at the top of the page because the slide is not actually visible on the screen. It says that we have to rewrite the square root of -a as I times the square root of a. Okay, this is what we must do first. So our first example, we were asked to multiply the square root of -6 times the square root of -10. Before I can actually multiply my radicand, since I have negative radicals, I want to rewrite this square root of -6 I'm going to rewrite that as I times the square root of 6. So just to make that a little bit clearer over here, the square root of negative 6, that's equal to the square root of negative 1 times the square root of 6. The square root of negative 1 is I, so we can rewrite this as I times the square root of 6. Right? So this is the process on how I'm actually going from the square root of negative 6 and writing that as I times square root of 6. Okay, but in short, we can just simply use this formula. Times, here again, I have a negative radical, so I'm going to rewrite the square root of negative 10 as I times the square root of 10. And now I'm going to multiply. So I times I is I squared. The square root of 6 times the square root of 10 is the square root of 60. Right, so I have I squared times the square root of 60. From our formulas for complex numbers, we had I is equal to the square root of negative 1. And then we also had I squared is negative 1. So I can rewrite I squared as a negative. Remember that all radicals must be simplified. So the 60, I can actually rewrite 60 is 4 times 15. So I'm going to rewrite the square root of 60 as the square root of 4 times the square root of 15. The square root of 4 is perfectly 2. So I'm going to bring down my negative. The square root of 4 is 2. That 15 has to remain inside of the radical. So the square root of negative 6 times the square root of negative 10 is negative 2 times the square root of 15. All right, there was another example, and we were asked to simplify the square root of negative 48 divided by the square root of 24. All right, so here again, before we perform any operations, we must take care of square root of negative 48. So I'm going to rewrite that by using the formula that was in the caution. I'm going to write it as I times the square root of 48 divided by the square root of 24. Now from this point, there's a couple things you can do. Remember that all radicals must be simplified. So you could simplify this radical, you could simplify this radical, or since we have 48 divided by 24, which is a whole number, I'm actually going to use something called the division rule for radicals. So I can actually write that as the square root of 48 over 24, okay, times I. 48 divided by 24 is 2. So we have our final solution as I times the square root of 2. All right, so just to keep things in these two problems, before you can do any operations, add, subtract, multiply, divide, okay, you must rewrite your negative radicals. All right, so I'm going to go back to our shared screen, and I'm also going to pull up the calculator. So while my calculator loads, you may want to grab yours. Okay, let's see if it's visible. Okay, there it is. Okay, so is everyone seeing the PowerPoint and the calculator on the screen? Okay, I think everyone is. All right, so now we're going to talk about operations with complex numbers. And here we're asked to simplify these three examples. Now, you can perform operations with complex numbers on your calculator. All right, I'm going to go into, we'll work these out by hand, but first I'll just show you how you can just sort of pop these things in the calculator. So for this first example, we're asked to add the complex number 3 minus 4i, so keep in mind that's a complex number in standard form, plus the other complex number, negative 2 plus 6i. All right, I'm going to turn on my calculator. And whenever you're dealing with complex numbers, I want to go into mode. And I'm going to go down to about next to the last line. And I'm going to take my calculator out of real mode and put it in A plus BI mode, which is complex numbers. Now, what this does is it helps the calculator understand that I is an imaginary unit. So it can actually input I. Okay. Now, this won't work if you are in your real number settings. All right. So now I'm in complex number mode. So I'm going to go back to my home screen, which is quit. So I'm going to hit second in mode, which is quit. And I'm basically going to enter in what I see, parentheses and all. So this first complex number has a begin parenthesis. I'm going to put it in as 3 minus 4i. So 3 minus. So remember, there's a minus button and there's also a negation button. All right, we're going to use that operation to subtract 3 minus 4i. Now on my calculator, I have this yellow I that's above my decimal point. So I'm going to hit second and my decimal point, and I'm going to close off my complex number. Plus, again, I'm going to use the begin set of parentheses. Here I have a negative 2. So I don't want to use minus. I want to use gate button. So that's negative 2 plus 6i. Right? And we get 1 plus 2i. Right? If we were doing this by hand, we would simply add our real numbers. 3 plus negative 2 is 1. We would also add our imaginary units. Negative 4i plus 6i is 2i. Right? I'm going to put in our second example. Negative 4 plus I. So keep in mind I'm putting in a negative and not a minus. Minus 6 minus 7i. All right, and we have a result of negative 10 plus 10i. And then lastly, we're going to multiply. Right, so I'm going to put this in exactly as I see it. 5 minus 4i. So notice I didn't put a times in actually, the calculator actually understands that parentheses denotes multiplication as well. So I'm not actually putting in a set of a multiplication. All right, and we have 27 minus 30. So the process will be the same if we were doing these by hand. If we were doing B by hand, we would subtract our real numbers. -4 minus 6 is -10. 3i minus negative, right, which is actually a positive. 7i is 10i. And in order to do example C, we would use the FOIL method. All right, we would multiply 5 times 35, multiply 5 times -2i. We would multiply -4i times 7 and -4i times -2i. We would simplify for the result of 27 minus 38i. So any questions about complex numbers? Now, as far as your calculator is concerned, if you're in this A plus BI mode and you're doing things mathematically, it won't affect anything. All right, so your calculator can actually, it can be in real mode or it can be in A plus BI mode. Okay, it can be any of these two modes without really affecting anything. All right, the only thing the A plus BI does is it allows you to enter I in the calculator. Right, so I'm gonna pull that down on the screen. And lastly, we'll talk about powers of I sort of briefly. These powers of I, here's a pattern, right? We talked about I was equal to the square root of -1. I to the first power is I squared is -1. I cubed is -I. I to the fourth power is 1, and then I to the fifth power simplifies down to give us I. Okay, now you can actually reduce powers of I. One thing about the calculator is that it does not handle these types of problems very well. So to give us a couple of examples along with the solutions. For this first example, we're asked to simplify I to the 13th power. Now, in order to simplify these things, you want to keep in mind the rules for exponents. Whenever you multiply exponents with the same base, you add your exponents. Whenever you raise a power to a higher power, you multiply. They're kind of using those rules here. So for this I to the 13th, it was written as I to the fourth raised to the third power. Right? Keep in mind when you raise a power to a higher power, you multiply. So 4 times 3 is 12. Times an I to the first. So an I to the 12th power times an I to the first power. Whenever you multiply like bases, you would add your exponents so that 12 plus 1 would give us 13. All right, so we've taken this I to the 13th power and kind of broken that out as I to the fourth cube times I to the first. Now from these given properties, I to the fourth power is equal to 1. So this I to the fourth power is substituted with 1. 1 to the third power is 1, and 1 time I is I. All right, so we won't really deal with these too much in the course. You won't even actually see these on the test. Okay, but I believe there are a couple of homework problems that deal with it. And then this last one, I to the negative third power. Notice that it's written as I to the negative fourth power times I. So here again, when you multiply like bases, you add your exponents. So -4 plus this understood 1 gives us I to the third. For the next step, they took I to the -4 power, and they written it as I to the 4 times -1, right? Because 4 times -1 is -4. On the next step, I to the 4th power was substituted with 1, right? 1 to any power is still 1, and then 1 times I is I. Okay, so I to the -3rd power simplifies to give you I. All right. All right, so if you have any of these in the homework, just kind of send me an email. I can go further in detail on these. And then lastly, we're going to talk about complex conjugates. This is going to play a role a little bit later on in this chapter. Up front, you just want to remember that all complex numbers have what's called a conjugate. So here's what a conjugate is. Let's say we have the complex number 3 minus I. Its conjugate is 3 plus I. The difference between a number and its conjugate is only the sign on the imaginary unit. Okay, that sign changes. And it's only the sign of the imaginary unit. If you were given a number 2 plus 7i, its conjugate is 2 minus 7i. All right, so notice from our number to our conjugate, the only sign change is with the imaginary number. And for -6i, its conjugate is positive 6i. Okay. So we'll take a look at these conjugates as they appear in the course a little bit later. All right. So any questions about section 3.1 in complex numbers? All right, next we're going to get into section 3.2. And normally in the course, this is where it starts to get a little bit fuzzy. Okay, because everything we've been doing up to this point you've sort of seen that stuff before, all right, in some form or fashion. But in this next section, okay, these are some like totally brand new concepts. So we're going to kind of play on some prior knowledge. We're going to talk about quadratic functions. And quadratic functions can be written in several forms. They can be written in what's called standard form. And standard form is actually the form that you see on the slide. P of x is equal to ax squared plus bx plus c. Right? That would be the standard form of a quadratic function. We also have something that's called vertex form. And this is the vertex form. A times the quantity x minus h squared plus k. So what we're going to do in this section, we're going to take quadratic functions that are written in standard form, and we're going to write them in this vertex form. Now, here's the thing about our vertex form, and I'm going to go back to our document camera. All right, so this would be our vertex form. of a quadratic. And I'm going to write this out as P of X is equal to A times X minus H quantity squared plus K. So if your quadratic is written out in this form, the vertex, you can simply pull it out of your form. It's going to be H comma K, right? You simply take whatever this quantity is, and that becomes H. One thing about H, though, is you will have to change the sign when you take your number out of your vertex form and actually write it out as, you know, an ordered pair coordinate. And you would take the constant on the end as K, and that would be your vertex. Right? The vertex is where your graph bends. Right? So if you have a vertex, if you have a quadratic that's U-shaped, your vertex is actually going to be at the crux of the U where it bends. If you have an upside down quadratic, our vertex would be here. Okay. Also from this form, I'm going to put a little star by this. We can pull out what's called the axis of symmetry. And the axis of symmetry would be in the form x equal to h. All right, so what is an axis of symmetry? Well, an axis of symmetry, if I take a look at this quadratic, for example, an axis of symmetry would be a vertical line that I can fold my quadratic over onto itself. Right, we can actually find the equation for that axis of symmetry. So we would simply take the h coordinate of our vertex, and that would serve as the constant in our equation for the axis of symmetry. All right, so these are two things we can actually pull out of this vertex form. Next, we're going to talk about a maximum and a minimum. Right? And a lot of these problems, you're going to be asked to give the minimum or the maximum value. The minimum or the maximum value is simply the y coordinate or the k coordinate or the second coordinate of your vertex. Okay. So I'm going to put that as a bullet point right here. The minimum or maximum value is the y coordinate and I'm going to put k in parentheses of the vertex. Right, so the minimum or the maximum value, the minimum or maximum value would be given in your vertex. All right, so this is the important things you can find out in your vertex, the minimum or maximum value, and it's always the second coordinate. All right, now how do you tell if you have a minimum or a maximum? Well, a lot of it depends on your graph and the way your graph looks. You have a maximum if your graph has an upside down U shape. You have a minimum if your quadratic has a U shape. So if you have a maximum value, remember that this is your vertex, and I'm going to call this h comma k. The k value is your. So here again, if this is your graph, your vertex is where your graph bends. That's in the form h comma k. Your k value is your minimum. All right. Okay, so any questions about this vertex form of a quadratic? Right, from the vertex form of a quadratic, you can easily pull out your vertex. That'll be given in your formula. You can pull out your axis of symmetry. Right, that's also given. The value for h is also given in your formula. And you can also pull out the minimum or the maximum. Keep in mind that the minimum or the maximum value is the k coordinate of your vertex. All right, so before we go on any further, we're going to talk about the vertex. And we're going to look at 3 ways to find the vertex. We're going to find the vertex by using a formula. We're going to find the vertex by using a calculator. And then we're going to find the vertex by putting our equation in that vertex form. All right. So we're going to find the vertex by using the formula. So here's the formula I'm talking about. The vertex is equal to negative b over 2a, comma f of negative b over 2a. And since this is a formula, I'm going to put it in a box. Now, if you use the viewing example homework, you're going to see this pop up. Some of the problems, they're going to find the vertex by using this method. Other problems, they're going to find the vertex by using the vertex form. All right, so first we're going to look at this formula. And it's negative b over 2a, comma f of negative b over 2a. So here is our example. In the direct, ask to find the vertex. And our function is p of x is equal to x squared minus 6x minus 2. All right, and we're going to find the vertex by using that vertex formula. So I'm going to just kind of write the formula underneath the problem. So the vertex is equal to negative b over 2a, comma f of negative b over 2a. Right, so I need a and b. So the way I find a and b is I go back to my quadratic function, and in order to use this formula, your quadratic must be in standard form. Right, so this quadratic is in standard form. Remember that standard form was ax squared plus bx plus c. So a is going to be the coefficient of your squared term. So a is going to be 1. B is going to be the coefficient of your middle term, which is negative 6. right? And then C is going to be -2. Even though we don't need it, I always like to write out A, B, and C. All right, so A is a coefficient of your squared term, which is understood 1. B is the coefficient of your middle term, which is -6. You must take the sign as well as the number. And C is -2. All right, so now how do we decipher this formula? Well, the x coordinate is simply going to be -b divided by 2a. So I have a negative, and that's from my formula. B is going to be -6 over 2 times a, and a is 1. Okay, so I'm going to simplify this. Let me pull out another sheet of paper. So that should actually simplify down to give me, or give us, a 3. Right? A negative times a negative is a positive. 6 divided by 2 is 3. So that's a +3. So now what about this other side over here? Then it says f of -b divided by 2a. Well, -b divided by 2a, it's simplified down to give us 3, right? So we have to find f of 3. So I'm gonna kind of put this step in. So this is what happens once all the dust settles. Right, so I took our formula, I substituted A for 1, B for -6. I substituted that into the formula. Right, I simplified -b over 2a to get 3, so I have 3 comma f of 3 comma f of 3. Right, so our first coordinate of our vertex is 3. So how do we find f of 3? Well, in order to find f of 3, we must go back to our original function, and we want to substitute x for 3. So I'm going to do that right here. F of 3 is going to equal to 3 squared minus 6 times 3 minus 2. So here's what I'm doing. I'm going back to the p of x, right? And in this formula, it's called f instead of p. F is just the standard notation for function. All right. So if we were to find f of 3, right, this is 3 squared minus 6 times 3 minus 2. So that's where this is coming in. All right, and now I just want to simplify. So 3 squared is 9 minus -6 times 3 is -18 minus 2. And I believe once all the dust settles on this, I get -11. So my vertex is 3 comma -11. So is everybody okay with using the formula to find the vertex. All right, now we're going to use the calculator. All right, so we're going to use the same problem, so we should get the same vertex. All right, so I'm going to go back to the shared, excuse me, the shared screen. And I'm going to pull up the calculator. Okay, I'll just pull up this calculator. So now here's how you find the vertex using the calculator. All right, we're going to use that same function, x squared minus 6x minus 2. First thing I'm going to do is go into, I'm going to turn it on first of all. I'm going to go into y equals, and I'm going to clear out any functions. And I'm going to put in x squared minus 6x minus 2. X squared minus 6x minus 2. And I'm on a graph by using zoom 6. All right. All right, so now this is a problem you may run into. In order for the calculator to calculate the vertex, you actually have to see where your graph bends. All right, so just notice that I can't actually see my vertexes off my screen. So from what I would do from this point is I would hit zoom and I would scroll down to 0 for zoom fit. What zoom fit does is it will fit the graph to your computer screen, to your calculator screen. Right, so you should be able to see where it bends. So that's the first thing. You want to graph it. If you can't see where it bends, you want to hit zoom 0, which is zoom fit. So now here's how you calculate the vertex. Now what I'm actually going to go through, there are a couple of videos that show how to find the vertex using the calculator, and I'll kind of direct you to those once we go through this example. All right, so if I'm going kind of fast, there is a video that kind of goes over the same exact concept. All right, so once we have the graph on our screen, we're able to see the vertex. I'm going to go into calculate. So I'm going to hit second and trace, which is calculate. Now notice I don't see a vertex function, but what I do see is minimum and maximum. If you look back in your notes, we talked about a minimum and a maximum graph. The graph is a minimum. And I'm going to go back to graph for 1 second. All right, we have a U-shaped graph. So notice that the U-shaped graphs are graphs of minimums. So this would actually be the graph of a minimum. So I'm going to go back into calculate. And I don't actually see vertex, but I do see minimum. So I'm going to press enter, right? If you had the graph of a maximum, you would press maximum to find the vertex. All right, so now once we're in this minimum function, we have to do a couple things. We have to put in what's called a left bound. We have to put in a right bound. We have to put in a guess. A left bound simply means that I must set a point physically to the left of my vertex. All right, so on my screen, notice here is my vertex, here is my cursor, and my vertex is right here. Since my cursor is already to the left, I'm simply going to hit enter. And notice that it pops up a sideways triangle, and it should fall to the left of your vertex. Once we hit enter, notice it asks for a right bound. So I'm simply going to move my cursor to the right of the vertex. Now, your coordinates don't have to be exactly the same as my coordinate, but as long as you're physically to the right, you can press enter. So notice there's another sideways triangle that falls to the right of your vertex. It asks for a guess. I'm simply going to hit enter. And we have our vertex 3, negative 11. Okay, now one thing you'll notice about the calculator, it's not exactly 3 as far as the calculator is concerned. It's like 3.0000, then this little 4 pops up. As far as the TI-83s are concerned, it's not actually a true 0 unless it's 0 to the 16th decimal place. Right, so you may see these little fudge numbers at the end. Right, but we worked this out mathematically, and we also found that the vertex was 3, negative 11. Any questions on using the calculator? And now while I have up the shared screen, I will show you where you can find the video that deals with the calculator. If you go to Blackboard to the lecture notes section, where I sort of pulled up the 3.1 and the 3.2 set of notes, there are a couple of videos. One uses the TI-83, 84, and one uses the TI-89, and they both go through that same process on how to find the vertex of a parabola. All right, so that's our second way to find the vertex. Okay, first we use the formula, which was a little bit complicated. Next we use the calculator. Okay, the only thing about the calculator is you have to know if your graph is a maximum or a minimum, and you have to see where it bends in order for your calculator to calculate it. All right, so lastly, we're going to take a look at using the vertex form to find the vertex. But before we do that, we got to talk about something called completing the square. Okay, because completing the square is involved in vertex form. So it says in order to complete the square, first off, you must have the correct form. You have to make sure that the coefficient of your squared term is a 1. If it's not a 1, then you have to factor out to make it a 1. Next, you'll add half of the middle term squared to both sides. Lastly, we can rewrite our completed square as a perfect square trinomial. And then we have what's called vertex form. Okay, now we're actually going to see an example of these steps in action. Okay, so I'm going to go back to our shared screen. Excuse me, I want to go back to our document camera. This is the shared screen. And we're going to work out an example. Now this process that I'm going through, there's a video for this one as well, and it's on the announcement section. Right. So now I'm actually physically doing this. I put the calculator vertex thing on the announcements, and there's this completing the square video that's on the announcements that we're about to go through now. All right, so here are directions. We want to write in vertex form we have p of x is equal to x squared minus 6x minus 2. So we're going to write it in vertex form, and then while it's in vertex form, we're going to pull out the vertex, the axis of symmetry. We're going to find the minimum or maximum value. All right. So this is in standard form. We're going to write it out in vertex form. So the first thing I want to do, we have to make sure that the coefficient of our squared term is 1. So we already have the first condition. The coefficient of the squared term is a positive 1. The next thing I'm going to do is I'm going to group my first two terms, my squared term and my first degree term. And I'm going to group those with a set of parentheses. So I haven't changed anything. What I started with is the exact same thing I have here. The only difference is a set of parentheses. Now we're going to actually complete the square. We always complete the square with our squared term and our first degree term. So I'm going to write this out as x squared plus 6x plus, and I'm putting in a blank. I'm ending my parenthesis, and I'm brought down my -2. Okay, this is the complete square term, or complete the square step. So how do you complete the square? Well, I'm going to take half the coefficient of my middle term. So if I have -6, I'm going to take half of that, so I'm going to divide it by 2, and then I'm going to square it. So to complete the square, take half of the coefficient, and coefficient means the number part of your term, and square. So I took half of the coefficient of my middle term, so half of -6 is -3. When I square -3, I get a +9. So that's why when you're completing the square, this is always positive, this last term. Right? Because if you square a positive, you get positive. If you square a negative, you get positive. Now, since we completed the square, we have added something that was not originally here. So if I go back and compare that to what I started with, I had an x squared. I started with that. I have a -6x. I started with that. I have a -2. I started with -2, but I did not start with this 9. So what does that mean? Well, the properties of equality tell us whatever we do to one side, in order to maintain equality, we must do the exact same thing to the other side. So since I added 9 to this side, I must add 9 to the other side. So it balances out. Is everybody okay with this step? We completed the square. Notice that when we completed the square, we added something to the right hand side, so we have to add the exact same thing to the left hand side. So now I'm going to take this 9 that was added to the left hand side, and I'm going to move it or transpose it to the other side. So now I have something that looks like this. P of x is equal to x squared minus 6x plus 9 minus 2 minus 9. Right, so I simply took this 9 that I added to the left hand side, and I basically subtracted 9 from both sides. Or I transposed it. I changed its sign and moved it to the other side. So it's like we added a 9 and then we're sort of subtracting out a 9. All right, now here's the final piece of the puzzle. Whenever you complete the square, you force a perfect square trinomial. So what do I mean by that? We can rewrite x squared minus 6x plus 9 as x minus 3 quantity square. Because if we take x minus 3 times x minus 3, we should have x squared minus 6x plus 9. Negative 2 minus 9 is negative 11. So this is vertex form. All right, any questions on where this comes from? All right, we had to complete the square. Kind of go back to this. All right, first thing we had to do is make sure that the coefficient of our squared term was 1. Since we had that condition, we grouped the squared term and the first degree term. These are the terms we need in order to complete the square. Next, we took half of the coefficient of the middle term and squared it to get 9. Since we added 9 to the right-hand side, we had to add 9 to the left-hand side. Then we moved our 9 to the other side, so we transposed it. Then we pulled out our perfect square trinomial from our completed square, and we simplified. So now, how do you pull the vertex out of this? If I go back to our first set of notes, it says that P of x is equal to A times the quantity x minus h squared plus k. So notice that our vertex is h comma k. So here's what you have to keep in mind when you're pulling the vertex out of your vertex form. this first coordinate, its sign will change. Notice that in my form, it's a negative h, but when I write it out as my vertex, that negative h becomes a positive h. So the same thing happens here for our vertex. And keep in mind, we found this vertex a couple other ways, and we found that it should be positive 3, negative 11, right? This negative 3, its sign must change to positive 3. Whatever our constant is on the end, that is our k-coordinate. So we have the vertex 3, comma, negative 11. Right? Any questions about the vertex? We can also find the axis of symmetry. So if we go back to our formulas for the axis of symmetry was x is equal to h. So in this case, h is negative 11. So the equation for my axis of symmetry would be x is equal to negative 11. Right, so this vertical line, x equal to negative 11, would be the line I can fold my quadratic onto. So now here's the last part of this. What is the minimum or maximum value? What is the minimum or maximum value? So first of all, is it a minimum or is it a maximum, and why? Well, keep in mind when we graphed from earlier, our graph looked something like this, right? It was a U-shaped graph, and when we put it in our calculator, we determined that it was a minimum graph, right? So this would be a minimum. And we can determine that just based on the U shape of our graph. What's the minimum or the maximum value? Well, remember from our formulas earlier, the minimum or the maximum value is the k-coordinate of our vertex. So the minimum value would be negative 11. So the graph is the graph of a minimum, and the minimum value is negative 11. Now, even though it says minimum, your minimum value can be positive, right? Your minimum or your maximum value is whatever the k-coordinate of your vertex is. Right. So any questions about the vertex form? Now, on the video that's on the announcements, I did do a different example. In that example, the coefficient was not a positive 1. So you can kind of see what takes place when the coefficient is something other than a positive 1. All right, so I did want to stop the recording.